Constant velocity. The purpose. The purpose of this lab is to analyze an everyday demonstration of constant velocity, then create a comparable model based on the analysis. Why do the results matter? These results can be used to predict future positions based on known velocity and position vectors in time. Video analysis. My experiment was rolling a 0.113 kilogram ball with a diameter of 0.0762 meters across a flat counter. Through Tracker, I was able to get quantitative data to use for my computational model. Useful quantities. From Tracker, I was able to deduce the ball's initial position at 0 seconds of 2.22 times 10 to the negative 16, 0 meters. The average velocity was calculated by using the final position minus initial position divided by the change in time. So the initial position was used as well as the second position at 0.033 seconds. With negative 3.73 times 10 to the negative 2, 0 meters. The average velocity was calculated to be negative 1.1300 meters per second. The ball's final position at 1.5 seconds was negative 1.36800 meters. The computational model. By using the useful quantities, I was able to fill in the lab script to create a computational model that could approximate future positions of the ball observed. The computational model utilized the fundamental principle in order to have constant velocity. So in order to achieve this, we use the momentum principle, which says F net equals the mass times acceleration. So to rearrange that, you get F net divided by the mass, and then acceleration can be rewritten as the change in velocity over change in time. So then you can get the change in time times the net force divided by mass equals the change in velocity, which can then be written as the change in time times net force divided by mass equals the finest minus the initial velocity, which can then be detailed as the final velocity equals the initial velocity plus change in time times the net force divided by mass. By knowing that the initial velocity and final velocity has to be the same because the velocity is constant, you know that the delta T F net divided by mass has to equal 0. And the only way for that to equal mass is for the net force to equal 0. And then because of this leads to Newton's first law, which states that a system in motion will remain in motion unless enacted by another force. So because the net force is 0, the velocity will stay consistent. So the graph. Here we have both the computational graph points and the video analysis points. Both of the graphs have a negative slope, but the computational model obviously decreases at a faster rate. The causes for this could be when I was doing the experiment, the ball was rolling in different directions, so I had to constantly redo it to get it to go as straight as possible, so that could affect the velocity and its consistency. Also, I threw the ball, so that's sort of harder to detect. And yeah. How to improve. If I was to do this again, I would definitely make sure that the ball was not shifting or anything like that. I would make sure it was going as straight as possible. I would definitely still use the same axis that was used this time because it was in the straight XY plane, so that made the most sense. As far as the computational model being useful, I believe that was a very useful model because it did use the initial and average velocity determined by what we observed. So I feel like it was the most accurate, but because of the situations with the surface and things like that, it of course was manipulated incorrectly. Thanks for watching.